All right, so we've talked about all of these amazing things you can do with multiple linear regression, and now we're going to talk about how we can make some choices about what we should actually be doing. So, more is better, right? Just throw the whole data set at a problem and it goes away. Unfortunately, that can't quite work. One, there's mathematical limits. This has to do with what we call degrees of freedom, and we'll take a look at that. Another thing is that overfitting is a problem, and we don't want to try to make a model that explains the current data perfectly but doesn't really explain the underlying relationships. And sometimes we even want things to make sense because sometimes we think we actually have to tell somebody about our analysis and explain our models. Crazy, right? All right, so let's start by talking about degrees of freedom. We talked about this before, that it's important when we have our model that we need some variability, and variability allows us to make choices. Degrees of freedom are like that. So think of, I kind of like this example, think of yourself as a fun-loving person who loves to wear hats. You couldn't care less what a degree of freedom is. You believe that variety is the spice of life. Unfortunately, you have constraints. You only have 7 hats, and yet you want to wear a different hat every day of the week. When do you have choices? On the first day, you can wear any of the 7 hats. You have lots of choices. On the second day, however, you only have 6 hats to choose from. On the third day, right, you can choose from the 5 hats. By the time you run out of days, you have no more choices. And that's what degrees of freedom are like. We need some choices, right? Because so we had 6 days where we had some freedom to make choices. And that's essentially what our models do. They need variation in order to make choices. We can't predict things if we don't have any information about them. And if we have no variation, we can't understand how one thing influences another. And so we need at least as many observations as we have variables. Which sounds easy in a big data world, but with some of the kinds of variables we've been talking about, you can grow your massive number of variables very quickly, and you could outpace the number of observations in your model and not give your model enough wiggle room to make decisions. And so we want to be careful when we want to pick an approach for how we might build up or tear down a model, that we keep in mind that we need to have at least one more observation than we have parameters to estimate, or variables we want to estimate. So trying to individually fit all possible combinations of variables is just too hard. Think about it this way. If you have 2 variables, how many models could you have? You could have one variable model, the other 1 variable model, or the 2 variable model. Okay, great, 3 models. What if I have 3 variables? Okay, well that's 3 single variable models, and then I could have any of those with the other 2 variables, right? So that's 3 times 2. And then I could have 1 3 variable model. So 6, right? So you get into, do you remember that from math, the factorials, right? We start to get into that the options become huge in a hurry. And we don't want to get, and so when we have 4 variables and we're talking about 4 factorial or 5 variables, 5 factorial, we get into, right, a whole bunch of 5 times 4 times 3 times 2 times 1. So 5 times 4 is, 20, 60, 120 models just with 5 variables. That's a lot of options. And trying to then, compare those 120 models manually is headache inducing. What if you have 20 variables, right? There's no way you can do it. So there's a couple of basic approaches that build towards the quote unquote right model. One of them is what we call forward selection. Here you start with nothing and you fit all possible single linear models and you're going to choose the best one. Usually you want to choose the best one in terms of r squared, or you can choose it in terms of the lowest p-value, but probably in terms of r squared. Because you can have things that have very little variation, so they have really tiny p-values, but don't explain much of the variation of the overall model. So you want to pick the model that does the best at explaining. And then you keep going. We'll get back to mixed selection. Backward selection works the way you would expect. It's the opposite. You take all the variables you have or are thinking of using, and you eliminate the least significant ones. And you stop when you have eliminated all the insignificant variables. If you don't have the degrees of freedom for it, you can't do this. So if you have a lot of variables and not a lot of observations, you can get into trouble trying to use backward selection. Mixed selection allows you to kind of take the best of both. And this allows you to start basically with a forward selection model. But as you go, sometimes you can add in a variable and the p-value of an existing variable drops it out of the model. So it can make p-values change as you go. And so you keep going, but you start dropping insignificant variables as you go along if that happens. I thought it was also worth talking about that we'll talk about things like lasso approaches later, which are kind of, I would say, like stepwise regressions on steroids, where instead of asking the computer to, just fit with the existing variables that I've thought of, we allow the computer to also multiply, add interaction terms, add transformations of the variables, and we allow it to essentially iterate on the model and decide what the best possible combinations of all of the variables are. And we get some really wacky things, but we'll talk more about that next quarter. But for now, if you want to do stepwise modeling, you don't even have to do it all yourself. You used to have to do this all yourself, right? So you'd fit the full model and then you'd start eliminating things, or you would fit all the single models and then you'd start adding things to them, right? And do stepwise modeling essentially on your own. There's still some value to some stepwise modeling on your own because the computer doesn't do a perfect job of eliminating redundant things, and it doesn't do a perfect job of dealing with some of the more, sort of complex interaction terms and things. Because if you include an interaction term, you need to include all of the terms relevant to it, and so you need to be careful when doing that in the stepwise model. But still, the fact that you can tell the computer to do stepwise modeling for you, and here's some code. It's available, by the way, in Databricks. And so we can do this stepwise modeling. All right. So how do we make choices if we're doing it by hand or want to compare things sort of independently? We've so far taken a look at R squared. And essentially, this is kind of like what we're asking the computer to do. But with R squared, bigger will always be better. More variables will always improve R squared. So what we do is we typically use an alternative approach of using adjusted R squared. At its simplest, this is a simple way to try to punish yourself for adding additional variables if they don't add value to your model. So comparing adjusted R squared kind of penalizes your R squared for the additional variables. Other approaches can penalize even more for these additional variables, such as Akake's information criterion. This is what the stepwise regression model uses. So did additional variables add additional useful information is essentially what this asks, and it has a process for doing that, and it measures whether it does or not. Or you can even, and you can also compare the Bayesian information criterion, which is even tougher on complexity. So the more variables you add, the more interaction terms, the more it punishes you. The ISLR book likes us to compare F statistics of the models as a nice way to check if it was worthwhile to add variables. And so we'll use the ANOVA command with the two models to get there. I have a handy dandy table for you with all of these approaches to validating models. What's the right one? What's the best one? Well, we're going to use them in balance. So you might ask, what does the AIC say? Is it getting lower? If the adjusted R squareds are close to each other, If you get some wild improvement in your adjusted R squared, these are related ideas. So probably the AIC is going to say, yeah, okay, that additional variable was worthwhile. But if the adjusted R squared improved just a teeny tiny bit, you might look to the AIC or BIC to say, was adding that variable really worthwhile? Or the F statistic, did I really get something out of it? Even if it's statistically significant to do so. The step approach sounds great, but there are some reasons why it might not be appropriate in all cases. One reason it might be inappropriate is that we might want to think about including insignificant but theoretically important control variables. So remember that we can never reject the null, We only fail to reject the null. Or we never accept the null, rather. We can fail to reject or reject the null. So Since we never accept the null, we never really say that the variable doesn't matter. We just don't have any evidence that these things do matter. So if they're theoretically important and we're worried about their influence, even if they don't come back statistically significant, we might include them just in an abundance of caution. So this might lead you to include more control variables than are significant or than the step approach would suggest you needed to include, especially if you're really worried about some factor X and its causal influence on Y. The other thing, though, is that we need to include variables that are dependent on each other. So you may get a case where when you're including polynomials, x, the coefficient on x is insignificant. Well, I still need to include x if I'm going to include x squared. So if x squared is significant but x is insignificant, you still need to include it in your models. And there may be some other reasons as well. In terms of thinking about these variables, another way you might think about is how much do you care about omitted variable bias? You want to be very careful with including things and making sure you include appropriate ones, right? Anything that could be correlated with X and Y, if you're worried about omitted variable bias, you might include. If what you're more worried about is how much you can improve your predictive power, focus on adjusted R-squared or those other measures for whether we're improving the goodness of fit and the explanations of our model. We might ask a question, do I have enough degrees of freedom to include more, right? We have our mathematical limitations, especially when we get to things like time series models. We often don't have a lot of observations, and we might need to think about those degrees of freedom very carefully. There's some more cautions too, and next time we're going to talk more about some things like bad controls. These are fun, so we'll have fun with bad controls. The trouble with P and P hacking, why P isn't the perfect measure of whether or not I should include additional variables. It's one way of thinking about it, but it has its dangers too, and we'll focus on that a little bit more next time. And in the part of this class is teaching you to lie with data, we'll teach you something about P hacking. And we'll also look at some other issues that crop up in linear models and how to correct them. So there's some cautions in how you choose and shape your models. But for now, and redundancy is also going to come up. But for now, we'll leave it at that, and we will talk more about more linear models next time.